Good morning, everyone. I'm Gowthaman Parivendhan. I'm a simulation researcher at IMR, and thanks for attending today's session on unlocking production excellence using mechanical simulations. So, before I go into the specifics of today's talk, I thought I'll introduce us a little bit. So, IMR is a leading research and technology organization. We have dedicated researchers working on digitization, sustainable manufacturing, design for manufacturing, robotics and automation, etc. So, our aim here is to help Irish companies to adapt latest technologies to enhance their production capabilities. So, in that regard, I'm going to show how simulations could be of help addressing some of your manufacturing problems. So before I answer why we need simulations, I'll explain what are simulations. Well, simulations are representations or imitations of a real event using mathematical models. So why do we need them? Well, they offer cost-effective outcomes for various processing conditions without having to physically perform the experiments or processes. And sometimes some of these physical parameters, they are tough to observe or measure using experimental setups. It could be expensive, it could be of a health and safety concern. So in those areas, simulations would be of help as well. So mechanical simulations, as I said, they typically solve a partial differential equation that describe the mechanism that we are investigating. And throughout this talk, I'll be talking only about physics-based models, the discrete event methods or process simulations or kinematic models are not covered in this session. So the most commonly used mechanical simulations are mesh-based, and that's because they cover most of the manufacturing problems that we face. And some of the common numerical tools include finite element method, finite volume method, finite difference, etc. But there are some scenarios where we need meshless methods like powder or granular geometry. And we treat each of these powder particles as a single entity. And in those scenarios, we might use methods like discrete element method or smooth particle hydrodynamics or molecular dynamics. So some of the meshless methods out there. So in the next session, I thought I will walk you through the workflow that we implemented in a project where numerical simulations played a crucial role in enhancing the process. So conformal cooling, it's a mold cooling technique in which we ensure uniform temperature gradient through the cooling process. So why do we need this? Well, in injection molding, when the part is cooled by the cooling channels, the non-uniform cooling builds residual stresses in the part. And when the part is ejected from the mold, it might deform. This, of course, is not desirable for the company. And also because the cooling channels put in effort in cooling the bulk of material as well, there's increased cycle time. So how can we address this? Well, we can do that by conforming the cooling channels as close to the part shape as we can. But traditional manufacturing methods are constrained in this regard because the path lines of these cooling channels are 2D in nature. And like these 3D conformal cooling channels can be manufactured by additive manufacturing because that's a layer by layer manufacturing technique, and we can easily achieve these 3D cooling channels. So some of the advantages of conformal cooling include, as I said, lower cycle time, and due to the uniform temperature gradient, we can minimize the part distortion and defects, and there's also reduction energy. And of course, we use simulation in finding out these conformal cooling channel performance, but how do we know if the simulations are right? So that's where we have to validate the model. So we have a test grid in IMR where we heat a test coupon to a prescribed temperature. And once it's heated to that particular temperature, it shoots out, and the cooling channels within the test coupon cool down the part. And we measure these temperature over time and compare it with the simulations that are run using SimCenter 3D thermal flow model. So once we validate this simulation, we can be sure that it can be translated to the actual part that we are going to investigate. So we also run polymer fill-in analysis using the NH Easy Fill Advanced environment. And the reason we do this is because it offers us a quick view of where the hot and cold zones are, where the potential problematic areas, etc. And based on this, we can design our cooling channels. We can either move the cooling channels closer to the hot zones or move it away from cold areas in order to achieve uniform temperature gradient. In addition to that, we also can detect short shots, and we can detect weld lines, air trap, uh, distortion, etc. And polymer filling tool also comes with extensive material database with all the widely used polymers out in the market. So we use the polymer analysis tool in tandem with SimCenter 3D to create these conformal cooling channels. Here I'm going to show you a case study that we performed for Tomat. I would like to thank Tomat for letting us share the case study for this particular demonstration. So here we have a insert used in injection molding, and it comes with these. We used conformal cooling channels to cool down the surface of the particle, and we initially started with the circular profile for the cooling channel, and then we moved on to other profiles such as square or parallelogram. And uh, again, I would like to emphasize that these parts can only be manufactured using additive manufacturing. It can be done with traditional methods, but then like it's going to be really difficult to achieve these profiles. So the reason we moved on to several profiles are ideally we need a straight line like this to achieve a really nice consistent cooling. But physically, that's not possible because for that to happen, we need just a single cavity that runs along the surface of the insert. And we start with the next thing, the circular coils that coil around the axis of the part. And we noticed that there is significant cooling on the surface where the circular channels are, but then there is increase in temperature between them. So this ripple effect kind of induces non-uniform cooling. So in order to address that, we have to either reduce the pitch, uh, so that will reduce the cooling errors, but then we compromise on the structural integrity. So the other approach we use is replace the circular channels with square profiles. And the square profiles, again, we notice there are issues between the channels. So that's where we use the parallelogram profile because the slanted edges of these parallelogram are exposed to the surface. So they kind of aid in cooling the surface a little bit more. And all these are done with the knowledge we gain from running numerical simulations in Siemens, SimCenter 3D. We then printed the parts, and early tests indicate up to 50% reduction in cycle time. So initially, the total cycle time was 32 seconds with 17 seconds of cooling time. And using the inserts with conformal cooling channels, the total cycle time was reduced to a little bit under 15 seconds, which in fact is lower than the initial cooling phase. So that's a really good reduction in time. So what does it mean? Well, it saves a lot of time for the company. They can now produce twice the number of parts in the same time. It can also save them energy and cost because they may not need to run two machines in parallel just to produce like n number of parts. They can just achieve it with one. And these are like some of the real impact that we achieved using conformal cooling channels in injection molding process, where simulation played a crucial role. And when we design these parts, we also have to make sure like it's structurally sound because these parts are going to be exposed to a lot of pressure and wear and tear, etc. So we run a quick statistical a study for these parts using the finite element tool in Siemens. That's SimCenter Nastron. And it has other potential applications as well, like it can be used for buckling, rotor dynamics, NVH, thermal analysis, etc. And it can also model various material behavior like plasticity, viscoelasticity, creeping. And it also comes with a really advanced parameter and topology optimization tools in order to improve your part design. So these are some of the features that in Siemens. And also, I mentioned additive manufacturing a lot, and we need to use right set of processing condition to print the part right in the first time. And this is often really difficult, and simulations can play a role in helping us there as well. So the Siemens additive manufacturing tool can help us define the part geometry on the build plate with support structure, and then we can run the simulation to predict the temperature distribution. We can know whether there'll be any pre-coated collision, well, there'll be any overheating in the layers, whether the part will distort before or after the support removal. And it also has a feature where it pre-distorts the part to create a compensated model. So when we actually print and remove from the support, it goes back to the original shape that we intended in the first place. So for example, the tool you see here, when we print this, because it is long and slender, it tends to peel off the support structure. So by using simulation, we can find the right orientation, the processing conditions, the location that we have to use in order to print it right the first time. So before I move on to the next session, I just would like to summarize some of the features that we use in NX. So Siemens NX is a really powerful tool. I just talked about some of the modules that we use in the workflow. It offers much more than what we showcased here. And also, it offers a unified workflow. By that, I mean, right from the design engineer to a simulation engineer, the technologist, all of us can use the same tool. And we can share the files without having to change the format. So it's a really powerful tool, and it's really easy to use as well. And with that, I will move on to the next tool. That's OpenFOAM. OpenFOAM is also one of my favorite numerical tools out there. It is an open source tool that is primarily used for computational fluid dynamics, but other areas of application include heat transfer. It is used in electromagnetics, acoustics. It has a really sound solid mechanics platform, and even it is used in finance, like they solve Black-Scholes equation to predict the commodity prices over time. So these are some of the areas it is used. And OpenFOAM versions, they come with a number of tutorials. And often we take the tutorial that resemble our problem at hand and we build on it. So it's a really nice feature to have at hand. And OpenFOAM is highly parallelizable. It is customizable and it's robust in nature. And there's also excellent support from the community. So just to illustrate what OpenFOAM can do, this is one of the analysis that we did in IMR. It's to simulate the furnace room cooling over 60 seconds. So we study how the air flows when the furnace is opened, and we include the buoyancy effects due to the temperature difference using Bose-Smith's approximation. So you might have seen this long name in the slide. So these are the names that are often seen in OpenFOAM solvers. So it basically describes what the solver is meant to do. And we use the inlet condition for the AC, which includes both the flow and temperature, and the temperature of the furnace, and study the airflow. Some of the similar applications include HVAC, aerodynamics, architecture, and in fact, urban planning. OpenFOAM also comes with a really powerful set of multi-fluid system. Like I said, the mesh methods, they often subdivide the whole area into smaller parts. And how it works for multi-fluid system is it calculates the material properties based on how much percentage of each material is in every cell. And we can include several physical phenomena like phase change due to solidification, due to melting, evaporation. All these physics can be included. Even species transfer from one phase to another. For example, transfer of CO2 from biogas to water during bioscrubbing process. These physics can be included in the solver. And some of the applications of multi-fluid system include bio and chemical reactors, fluidized beds, mixers, etc. So this is one of the classic examples from the multi-fluid tutorial cases in OpenFOAM. It's a water breaking over a dam with the surface exposed to air. So as you can see, like the interface is captured very well in detail, and it can in fact be translated for multiple fluids with all the fluid interfaces captured, etc. So that's the OpenFOAM multi-fluid system example. And where did we use it? We ran a quick gas enclosure simulation where we model the simulation of argon gas fill in the AM prototype enclosure. So we used a volume of fluid method to track the inner gas and the air phases individually. And we used that to know what should be the flow rate of the gas diffuser, where should be located, and whether we can maintain a layer of argon over the test specimen all the time. So these are some of the things that we are looking at while running the simulation. So again, this answers us a lot of what if questions instead of physically loading the material onto the enclosure and see it. Another example of OpenFOAM multi-fluid system is the mole fill foam. So this is a customized solver that we built entirely at IMR. So this is used to model polymer filling in injection molding process. It's very similar to EasyFill, and we use non-Newtonian assumption for polymers. We use temperature-dependent thermophysical properties, etc. And we also built custom boundary conditions for flow, inlet, convection, thermal loss, etc. And the reason we have this is to data transfer data to other applications like Grasshopper for the processing. And like I said in the earlier slides, OpenFOAM is highly customizable. So if we have a particular set of problem, physics that is not addressed by some software, like a lot of software, then we can be included and simulated using OpenFOAM. So that's what I meant by customizable. And the Solids for Foam was the solid mechanics platform I mentioned. While most of the solid mechanics solvers are based on finite element method, this one is based on finite volume. And it is a standalone toolbox for solid mechanics models. And it is compatible with both OpenFOAM and FOAMHSIM. And it is actively supported and developed at UCD and also from contributors around the world. It includes all the material models like thermoelastic plasticity, viscoelasticity, and also a sound fluid structure interaction solvers like shown in this example, where you see a flow of fluid over a flap. So these are some of the features included in Solids for Foam. And because I was talking about OpenFOAM, I also thought I will discuss a little bit about SimScale. SimScale is another tool that we use in IMR, and it's a cloud computing software that offers cost-effective simulation solutions. And it is based on solvers like OpenFOAM, Codaster, Calculus, etc. They also have their own niche set of utilities in SimCenter. And again, it has a wide range of application and fluid, structural, thermal simulations, and couple systems as well. And it comes with a graphical user interface for the simulation workflow. So the reason I included SimScale is if there are anyone interested in running a case on a solver like OpenFOAM, but they are not really keen on using Unix-based or Linux-based terminal approach, then SimScale offers a wonderful alternative as well. So with that, I conclude the solid and fluid cases. So all the topics I showed so far, you can assume the material to be one single continuous medium. But what about powder or granular media? Because they're not continuous. Like as a whole, the powder system behaves like a fluid, but then like each individual particle is a solid. So can we really assume it as a continuous media? Well, if not, how can we model it? So this discrete element method is one of the numerical methods that model the interaction between particles. And how it works is the total force on every particle due to collision with other particles or cohesion, body forces such as gravity or magnetic field are calculated. And using the force, the velocity and the new position of the particle over the entire time is simulated. Has again like wide range of applications. ranging from powder metallurgy, which is of particular interest to us in IMR because we handle a lot of powder systems in the additive manufacturing machines here, and like powder behavior in pharma and chemical industries, also in agriculture and geotechnical industries such as soil compaction or plowing simulations, etc. So Lights is the tool that we use in IMR for discrete element method simulations. So it is an open source tool developed by DCS Computing. And here you can see a couple of simple examples where particle systems are modeled for the flow on a conveyor belt and also mixing of particles of different sizes in a rotary drum. So these are just a couple of examples where lights is used. So it's again highly parallelizable, and it also comes with a smooth particle hydrodynamic solver. And it is again executed by a terminal like OpenFOAM, but the scripts are easy to interpret and modifiable. And complex geometries like the production assemblies of the rotary drum, for instance, can be imported as STL as long as it's clean and of high quality. It can be imported and used in the simulation. And they also have a platform where they can couple lights with other CFD tool for resolved and unresolved fluid particle systems. Some of the capabilities of this particular software include different material models to simulate various powder morphologies. For example, wet sand wouldn't behave the same as dry sand. So here you can see in the simulation that the wet sand tends to pile up more than the dry sand. So for this, they use capillary bridge models to simulate the water bridges between the particles that kind of stick the particles together to each other. And also they have material laws that define dry cohesion in powder systems as well. Again, these can be coupled with other numerical tools to provide realistic multi-physics simulations, like powder bed fusion, for instance, where there's a powder system where we also have to study the flow model. Asterix is their commercial version of the tool, where we can also model non-spherical particles like tablets, capsules, etc. And they offer much more in this commercial version as well. So here's an example where a DEM CFD tool is used in tandem. So discrete element method was used to create the powder bed in powder bed fusion process, and then CFD OpenFOAM CFD tool was used to model the melting of powder particles and then the flow and subsequent solidification due to the laser irradiation. So these are some of the examples where coupled simulations or standalone tools were used. To summarize, well, simulation is a really handy tool to have in early stage product development because it can answer a lot of your what if questions without having to build a prototype or a JIT. And simulation can also provide insight into the physics that take place in the process. And also, even if you have like a existing system, it can indicate any potential time or cost, performance savings, etc. So thanks for your attention, and I'm happy to answer any of your questions.
Great stuff, Gowthaman. Thank you very much for that. Was that a lightsaber at the end? Lightsaber?
I descended like that, yeah, indeed.
Yeah, well, look, when you're looking at 50% reduction in cycle times, you can see the value of this. We've a couple of questions in, so I'll get you to stay on. First question here I have are open source softwares reliable?
Open source softwares are reliable in my opinion. There's a widespread idea that they may not be. It is widely used in academia, and it is also like using also open source tools. You're in direct touch with the developers, and there's huge support from community. And one other advantage I see is in many of the open source tools, you can see what is happening in the background. You can access the code, so like it's transparent, and you can modify it as well if at all there is any bug. But in my opinion, it is reliable.
Great, thanks very much. Is there funding available for this?
Uh, yeah, there are like certain funding schemes that we can look at to help the SMEs run simulations. We are happy to discuss further. Feel free to reach out to us, and I'll actually share the contact details here. And Yeah,
Perfect.
feel free to reach out to us and we can explore other funding opportunities. Yeah.
We have another question in here. Can I run simulations on my desktop?
Yeah, we can. Most of the modern day systems are powerful enough to run simulations. Some high fidelity models, like realistic models, may take days to run, but still it can be done. And also there are other ways we can run simulate high powerful simulations, like using workstations or getting access to some of the national clusters like iChip, etc. So yeah, again, feel free to reach out to us and we can point you in the right direction if you're interested.
Perfect.
Yeah.
And another one here. How do you bridge, or how can you bridge the gap between simulation and reality?
Yeah, that's an excellent question. So that would be using the experimental validation, like I discussed in one of the slides before. So we use experimental test beds to because we know like what's happening for sure, and then we validate our simulation models using that. And once we validate the model, we can translate that to the unknown with the idea that it's validated for what we know. That's how we can bridge the gap between reality and simulations. Yeah.
Brilliant. Thanks very much, Gowthaman. Really insightful presentation. And
Thank you, Gary.
that's it for the
Yeah.
questions. Um, that's all from us. We'll be back in October for another webinar. Thanks again to Gowthaman, and thank you all for joining. See you soon and have a great weekend.
Thanks, Gary.